Hangout on air is live. All right, we're live. And we should be starting in just a few seconds. And let me, I think I should also make some banners and stuff, you know.
Banners, yes. Mm-hmm.
Okay.
It's 11 o'clock.
It's 11 o'clock. There's my computer. So.
And we are live.
We are live. Welcome all. This is the weekly hangout we do on LunarCubes every Tuesdays. Today's event ID is 14/05/27, which is essentially 2014, May 27th. And my name is Abraham, and I'm the host of this program, and I have the co-host Michael with me. And today we're going to have the topic Deep Space Information System, which Michael Riley is going to be presenting. All right, Mike, and I think I turn over the stage to you, and you're on the air. Say hello and get going.
Very good. Thank you, Abraham. Today we're going to go over some ideas associated with the Deep Space Information Systems well, it's our own project, connected with the LunarCubes networks concept. I have been involved with various kinds of spacecraft missions and mission concepts since about 1998. So we're coming up on, well, we'll be coming up on 20 years in just a few more years. The focus that we're talking about here is enabling new technologies and development and exploration of the moon. The focus of my remarks today are going to be on what we need to do in order to analyze and understand the architectural options for realizing a network of assets and capabilities around the moon. Again, our vision at Flexure is an expanding web of cislunar service providers and users devoted to the exploration and development of the moon, and hopefully to other parts of the solar system as well. To draw some analogies with current concepts that are extant in the information technologies world, we have a lunar cloud of services where different spacecraft are providing different services to each other. That could be computation, communication, sensor webs. These could be services in lunar orbit, or perhaps, or definitely on the surface of the moon as well. The lunar web provides the connectivity and discovery mechanisms for connecting those different services together, and everything is riding on the various nodes, the actual spacecraft. It could be conventional spacecraft or cube-enabled technologies. And a cube spacecraft is a particular form factor which has become more and more popular as a way of getting spacecraft into space. A 1U cube is 10 centimeters on the side, and it's a convenient way, it's a convenient metric to design to, and it's been a way to open up new opportunities for getting things into space. Now, the nodes that we're talking about for the lunar networks, they're certainly associated with spacecraft, but an individual spacecraft can have multiple nodes just as it can have multiple computational or sensor resources. So that's the vision. And the important question here is, how do we organize these different assets to create capabilities? Because you're going to have a conventional spacecraft, you're going to have a bunch of spacecraft actually going to the moon in upcoming years. Some of those are going to be conventional, others are going to be cube spacecraft. You're going to have orbiters and landers, and it would be great to be able to take the excess capacity, the extra communication, and storage capabilities of those different spacecraft. It would be great to be able to synthesize those into extra capabilities. For example, once your main mission has been completed, your spacecraft is generally able to do more. And we want to be able to tie those together into doing interesting things. Just a few examples here for exploration. You want to be able to put imagers and spectrometers and wave field sensors into the lunar environment, cislunar and on the surface as well. And it'd be great to be able to design a specialized spacecraft, specialized rovers that focus on those particular mission goals, so that you don't have to build a generalized spacecraft and make a lot of trade-offs. You can just plug into the lunar network that's already there. The development goals, those are I put down here: engineering and technology. For example, how do we relay communications? Perhaps we can even relay power for some of the spacecraft, because if you have a very small spacecraft, it can be very difficult to have the collecting area to produce a lot of solar power. But perhaps you can put out an antenna and receive some power sent to you by microwave. And power beaming ideas are undergoing a lot of research right now. Command and control is going to be very interesting when you have lots of assets cooperating in the lunar environment. And the lunar environment is a great analog for doing things elsewhere, for developing various technologies, improving orbiting technologies, spacecraft working together, hopping, roving. Fundamental to systems engineering concepts is how do you get the mass, information, and energy where you need it, when you need it. It's a bit of a logistics problem, but that's the fundamental questions that we deal with when you're talking about aerospace systems engineering. And we really need a method for evaluating different solutions to these different problems. The main problem being, how do you explore and develop the lunar environment? How do you evaluate different possibilities? And how do you take advantage of new capabilities? How do you determine how to fit in existing or upcoming capabilities? So how do you evaluate all of that? Especially when you're starting from a situation which resembles this for conventional deep space, where it's essentially mission focused. You have one mission, you have essentially one asset. It's already hard enough to talk to the spacecraft, which is far away in deep space, and roughly the definition of deep space is far enough away from the Earth that you can't depend upon many Earth assets. It's a special case, in other words. So you're really focused on building a spacecraft that can operate by itself if it can't talk to Earth for a little while, and you want to make sure that it's a very focused mission and not too complex, or you run into difficulty making it able to take care of itself for a little while. You want to, when you're putting together a deep space mission, you have some big questions. Can you reuse infrastructure, or do you have to create new infrastructure? And by infrastructure there, I mean the communications assets that will reach out and talk to the deployed asset. And it's really an end-to-end pipeline. You have the command and control infrastructure, you have the data downlink and data archiving, and eventually how you provide the data and information to the end users, the stakeholders that put together the funds and resources to put the asset out there in the beginning. Problems with this sort of stovepiped approach are that goals evolve. If your science mission is successful, you learned something, and now you have to move to a new set of questions, which means that you have to have a new solution to the new problems that were posed by the old science mission. So in general, your questions become more nuanced. These sensors have to become more focused and more specialized, or perhaps you need to tie in multiple sensors in order to get a better answer. So your mission starts to become more complex, has to become more capable, and then you start to run into the issue that, well, if you have a single platform out there in deep space, you have to trade off the different demands being placed on you by the different sub-goals, the different stakeholders that are partnering to put your space mission or your science mission out there. So the fact that you have a single spacecraft starts to make things more complex as well. You can't design an optimal deployed asset for a particular aspect of your mission. When you start to move into developing, for example, lunar space, a whole new set of technologies opens up. For example, it becomes easy to put nodes, these little 1U and 3U and 6U spacecraft into the lunar orbit or onto the lunar surface. All of a sudden, you have the ability to make specialized spacecraft that can be focused on performing a particular service for you. And these deployed assets can take advantage of an infrastructure, things that are already out there that can provide services. It takes some organization, it takes coordination, but when you take that qualitative step away from the stovepipe to an entire network, it enables specialization. It makes things more flexible, and you can get higher performing assets as well. But it's something new. We're talking about moving away from a mission focus to a focus where every time you put an asset out there, it actually can expand the infrastructure itself. And there you're asking something new for mission systems engineers and of the stakeholders as well. You have to figure out what's in it for them. What's the benefit or value for a mission planner to make his particular asset interact and interoperate and work with the infrastructure. We think that it's a win-win situation because the asset can build on the infrastructure and provide new capabilities and make the infrastructure even more valuable. You can call that the web effect. It requires a capital layout, though. It requires that buy-in that I was talking about. It's essentially untested technology. So bits and pieces are being tested here and there, and on the ground, you can argue that we have great examples of the web effect going on. But with an inherently multi-spacecraft system like that, where we really want the different spacecraft to be operating with each other, that's something which is going to be fairly new, particularly with the way that current spacecraft are operated. Spacecraft have a very limited amount of autonomy, and they get that mainly by focusing on their particular mission. So how you would have the spacecraft, how you would automate the capabilities of the spacecraft to relieve some of that ground-based interaction is going to be an important part of realizing the vision of the lunar networks. Take a look at the information systems that are involved. Essentially, with the conventional approach, you have essentially a pipeline, and you take a look at different aspects of your pipeline and try to size everything so that it fits into your various resource and money budgets. It's an end-to-end analysis. You're looking at the latency and bandwidth. You can't always talk to the spacecraft. You have to talk about communication opportunities. So the spacecraft have to be by themselves for a while and be available to talk to you on an episodic basis, which brings in a scheduling problem and getting back to providing value to the end user. How do you archive and distribute? And that's all pretty much part of the conventional process of putting together your mission. When you go to a networked system, particularly a lunar networks system where you have a networked architecture, you have a number of different considerations which are coming in. For example, routing becomes a much more complicated problem requiring a more sophisticated approach. You have delay and fault tolerance on the pipeline side, but on the networked side, it provides other complications for you. you open up a wider range of architectures to be considered, and I would say that you also require more autonomy, because at the very least you're going to have the deployed assets know where their neighbors are, so that they will know where to point their antennas in order to make those cross links between each other. And again, a bunch of these technologies are being tested piecemeal. However, we haven't gotten to the point where you have a deployed platform that you can start to lay your networked information systems on top of your hardware and communication levels. Which brings us to one of the main points that I wish to make today, is that modeling and simulation is going to play a key part in developing an understanding and some confidence in how to put together this new infrastructure, the lunar networks around the moon. And currently, modeling and simulation is already a critical part of our mission design and operations. And a quick definition of what a model is that I like is that it's an expression of your understanding of the system, and it's generally a particular aspect of your system. You have a question that you want to address, and you use a model to capture what you know about the system and its behavior. You use that to either address the question or to raise the question. And for example, some of the things that you use modeling and simulation for choosing architectures, for trying to estimate the performance of them, design and implementation make heavy use of models. Operations design and test, for example, when you're putting together command sequences, you often use modeling to make sure that the command sequences are going to do what you expect. Also, you make wide use of modeling in diagnostics, status determination, prognostics, where you're taking multiple streams of information and trying to get your best idea or best understanding of what the system is currently doing. Historically, again, models are generally domain-specific. They vary widely in the fidelity and sophistication. You have models that you use to estimate costs. You have models that you use to estimate the business impact of a particular system, all the way to the various domain models, the communication linkages, thermal models. So they're widely used in a wide range of domains to answer the different questions that come about when you're designing one of these aerospace systems. So again, there's a wide range of tools for answering these different questions, but essentially they're silos. Generally, when you're trying to put together a coherent design or a coherent architecture, you have a bunch of questions which depend on information, which interdepend on these different domains. You have to get questions to go from one domain and get answers from another domain. And that is where a lot of the process of systems engineering and design gets pretty hairy, and it becomes much more of an art form. A lot of times what you have is you have your domain engineers working on particular questions, and then you bring all the domain engineers together, and then they discuss and go over the interfaces and the interconnections between their different models. So essentially they use human techniques, wetware, in order to manage the interfaces between these different domains of knowledge. So we can go into a wide variety of the legacy tools, satellite or spacecraft toolkit, various sorts of orbital and astrodynamics tools, discrete event simulators, and there's a lot of institutional knowledge across the country with different companies, national labs, military, and so forth. Again, a lot of the action occurs at the interfaces, and I'm picking out the interfaces in particular because that's where you pose the problems, that's where you pose the questions, and that's where you have your information flow that you're trying to get together. So with our lunar networks, vision, there are new problems to understand. You have a multi-body problem. You're moving away from a conventional single deployed element or simplified multiple parallel elements out there that are each being controlled independently. We have multi-element interactions that you're talking about. You have command and control issues as well. One line that I'll keep coming back to again and again is that for multi-spacecraft systems, they have to be no more costly or complex to operate than single spacecraft systems, or else you're going to bury yourself in operational costs. Again, faults and the unexpected are going to have much greater impact on multi-spacecraft or multi-element systems. So that's something that needs to be understood, and you have to build some confidence in that. And also, you're not going to be able to go back and use your keep it simple stupid approach, a very focused approach, because again, you're making a qualitative jump to a multi-spacecraft, multi-element system. Because that's what the complexity of the solution is requiring. That's what your solution is requiring. Really, what you want to do with the lunar networks is that you want to be able to synthesize services. You want to have a mission. You want to be able to pull together different capabilities that are already out there, maybe add your own capability to that, and use and synthesize a way to meet that mission goal. Of course, out in space, going around the moon, there are a bunch of questions there. What's the value in it for the different participants? The way we're going to develop that confidence is through extensive modeling and going out there, doing some, and then improving our models. However, take a look at the sort of modeling that you're going to need. It's multi-domain. You have business, you have technical, you have orbital, you have the structural, everything that it takes to get a capability or capacity out there. And you're going to be able to need to federate the different models that you're putting together, because you get a question, you put together a model to help you address that question and maybe answer it, and then you have different ones that you need to pull together to address coherently the entire system. And also you're going to need to be able to deal with variable fidelity, because you're not going to be wanting to simulate every nail and cotter pin for the entire lunar network every time. However, there are some questions that's going to raise as well. And again, there's some work that'll need to be done in order to realize these distributed networks. However, there is hope, and there's a lot of developments that's going to make this doable. You need this new multi-domain heterogeneous modeling, but that's a problem that people have already started to run into here on the ground in a variety of different contexts. Overall, the trends are good. There's a broad COTS penetration for modeling and simulation in a wide variety of fields. You're using them in business, you're using them in technical fields, you're using them in building and architecture, civil engineering, using them to understand all sorts of networks, biological networks, business networks. We're learning more and more about how to put these models together. So there's a broad commercial penetration across the entire intellectual establishment, if you will. There's a steady evolution of modeling tools and capabilities, also standards and interoperabilities. A lot of these have come about because of people trying to make services available on the web and putting different services together. A lot of these service-driven advances involve knowledge sharing and the semantics of the underlying services and the data that people and machines are trying to exchange with each other. Model federation and synthesis is an important part of that, and also model analysis and checking. You want to be able to have something to help you figure out whether two model components are actually reasonable to use with each other. There's an old saw in aerospace and engineering that a lot of the models that have been developed in aerospace have been developed with a set of assumptions which may or may not be clear. For example, one shop has developed a lot of analysis techniques based on spinning spacecraft. And for some scientific applications, a spinning spacecraft is a fantastic way to go. Other shops may specialize in three-axis stabilized, which are good, for example, if you have an imager that you need to point somewhere. If you ask those two models, if you ask those two styles of models the same question, they'll come up with radically different technical answers to the solution. And if you ask the wrong question, you may find that you were quoted a cost or a resource use which just completely destroys your mission concept. And it may not. So somehow you need to be able to step back and ask the question, well, let me compare the spinner versus the three-axis stabilized. That's where you're starting to get into the model federation, where you have a way to not just choose models developed within a particular context, but be able to understand the context as well. So I think there was a conclusion here. I think we were there. Oh, let's see, where are we? Modeling simulation. There's the hope, and here's the conclusion. As space infrastructure and development and architecture design requires a new approach, you need to move beyond the single element analyses. And you also need to be able to bring, you need to be able to make more explicit the context of those mission analyses. You can't just have that in the domain expert, or else it's just going to be in the domain expert, and the human link in there will be the weakest link and slow things down. So we need to be able to capture that information and share that in order to federate the models. We have excellent legacy tools available. However, again, but these are silos and will add to the latency and misunderstandings unless we explicitly are able to capture the context and be able to bridge between the different domains. New technologies are available for that sort of knowledge sharing, and we're ready to use them. We've done various amounts of research. People associated with Flexure have experience with DARPA-supported techniques, and also a variety of analysis methods as well in a bunch of different engineering domains. A lot of the technologies have been driven by knowledge sharing needs and information technology, and we can just import those knowledge sharing concepts into the particular application, which is to realize the lunar network's vision, in which we can start to put together these multi-domain heterogeneous modeling capabilities so that we can analyze these potentially rather complicated capabilities that we want to put together. Essentially, we want to put a web together around the moon and perhaps beyond to synthesize exploration and development services in the cislunar environment. That's the conclusion, and I'm ready to entertain questions.
Michael, that was pretty good. And, okay, so help me understand if there is any focus issue, like when the traditional mission-oriented focus versus now multifunction aspect that we are entertaining, and the information architecture, do you think that's going to be substantially more complicated, or do they cross paths, or in view of one versus the other, they change priorities of some kind? Can you kind of give me about the mission architectures versus the information architecture needs, changing needs, if there is any?
The critical element is maintaining command and control of your deployed spacecraft, and that is the key and mission critical element that you are focused on when you're putting together your mission architecture and your mission design. If you lose contact with your spacecraft, the mission's done. If you lose control of your spacecraft, then your mission is done. So when you're putting together a networked architecture where you're relying on the deployed assets to maintain a synthetic service, like a service web, like a sensor web, you have to build in a very high degree of resilience so that your synthetic capability can withstand the things that tend to go wrong in space. So that's so your question, what does it change your priorities? Does it change your emphases? There is so little margin in the aerospace environment that you're always dealing with things on a remote control basis. You can't go out and wiggle the wires or move the wires from one place to another. So that raises your focus on service provision to a very high degree, because a lot of times when you lose a particular service, you've lost the mission. So there's a trade-off there. When you start to talk about multiple asset missions, multiple spacecraft missions, you would think that you can relax some of your constraints a little bit because you lose one particular spacecraft. You can have a failover situation, which is very familiar from folks in the IT field. So that's how some of your engineering focus is turned, because space is pretty unforgiving. Everything's remote. Physical access to the remote asset is essentially zero, and you're just doing everything by wireless. One way to look at it is that if you think about the number of times we used to reboot our wireless routers, if you can't reboot the wireless router, the mission's over. That asset is gone. So when you're building your spacecraft, when you're building your space information infrastructure, it has to be resilient to that. It has to depend upon watchdog timers and reboot the wireless router itself. The next level of constraints are going to be resource constraints, because everything is so far away. And when things get far away and you want to get the communication bandwidths up, that's going to drive your power costs or your energy resource costs, which is going to drive the matter, the mass costs, and the solutions that you have to your problems start to become too expensive for your budget. And so you have to rework the parameters of what you're trying to do in order to try to fit within your resource envelope.
Okay. When it comes to architectures that support and promote resilience and fault tolerance, I'm not sure, because I was also sitting in the who is this? South California. JPL had a flight software workshop, and I was there, and the way they described Mars, they did not talk about it, or they did not touch on it about whether that was driven with multiple processors, like in a water system or like a high-level dual redundant system. They did not talk about that model at all. It always appeared like a single control system. Do you have any views or change in trends or any preferences for the scale that we will be working with? Do you have some insight to it, please?
Your question is about processors and processing capability on board spacecraft?
Yeah, building in resilience with redundant hardware and redundant or like a fault-tolerant softwares.
Right. There are a couple of different needs that you're talking about when you're talking about resilient computation. There are various sorts of radiation effects, single event effects, for example, that can cause processors to suffer various faults, either to memory or to the computed logic themselves. And there are a number of different techniques for building fault-tolerant or radiation-hardened or tolerant devices that address various kinds of faults, and you can use them to build a tolerant system. If you take the penalty in computational speed and cost, you can get a radiation-hardened component that will be pretty resilient and will give you your computational bandwidth, but you'll have to fit within that bandwidth. Some folks have tried, and I was part of some efforts, to increase the bandwidth available on board spacecraft by using various commercial components, and do things like three-way voting or redundant synchronous computation or software implemented fault tolerance in order to improve the computational bandwidth that you have available for different tasks on board a spacecraft. What you need to do is that you take a look at what your spacecraft or what your mission can tolerate in terms of faults or potential errors. Okay. If you have a human system involved and you need a very high degree of reliability, maybe you'll do four-way testing of a radiation-hard, four-way voting on a radiation-hardened device. If it is a scientific, it's a high bandwidth scientific data processing. For example, you're running a pattern matcher against what amounts to noise, and you're just going to get a new batch of noise in on the when you fill up the buffer again. Then perhaps you can get away with using a processor which is less hardened to radiation faults and is faster, and also most likely it's going to be cheaper too as far as cost goes. So you need to look at what the goals are for that particular element and figure out what's in your budget and what you can tolerate. If you're flying a whole subscription of CubeSats and you're flying one a month, and the overall lifetime of the mission is not all that long, then you don't need the gold-plated or diamond-plated processor to keep things going. You balance things within your resource envelope and put together a coherent solution. The trends, I couldn't say what the current trends have been, but people are getting more experience with commercial devices into space. You've reached some fundamental limits in device size, and so you're starting to get into how different processes in the CMOS process work and how tolerant they are to various kinds of radiation that you receive in space. And they're a bit more radiation tolerant than you might expect. However, they still do suffer the single event effects. But really, NASA and other places regularly test electronic components, and they put them into space, and that's one of the things that the CubeSats are good for too, is testing out these various components. And you build a library of how the different components work in space.
Okay. when we talk about the information system, uh, do we have some views towards various hierarchy which address the mission goals or the infrastructure components? Have any some thoughts on such a hierarchy if it's applicable?
Well, what you're really trying to do is that you're trying to move the infrastructure architecture out into space, so that the things that you do on Earth to make things automatic and discoverable and provide the different layers, like in your OSI layers in your network, different levels of your networking, you're trying to provide more and more of that onboard the spacecraft out in space, so that you can do things like your automatic routing, across across your constellation of spacecraft. That's that's the direction that you're trying to go, so that when you put your spacecraft out there, you can take advantage of those different capabilities. You're no longer dependent upon assembling those on a mission by mission basis. And there's been some efforts to consolidate and make it possible to use different capabilities from one mission to the next, some sort of multi-mission architectures or multi-mission usages. And what we're going after here is trying to take what we know about how to put together those hierarchies, take what we've learned from the Earth, and see how we can translate those into the deep space context.
Interesting. Thank you for that. And also, you had if you mentioned about command and control.
Yes.
Do you think eventually our deep space information system will support automated, semi-automated, and the traditional models? And how would we do that?
Well, right now, spacecraft act a lot more like the remote-controlled toys that you get at Radio Shack, with a bunch of autonomous logic built in. So they are able to take care of themselves, and they are able to make their own decisions to a very limited extent. But it's all very carefully focused and disciplined, because a small error can render that deployed assets useless. So they're very careful about that, and when you're engineering your design, you design it so that if it reaches a problem that it can't handle on orbit, it calls back home and goes into essentially a safe mode. The trend over the past decades, as computational bandwidth has become more abundant in space, and our ability to handle various kinds of rules loaded on board the spacecraft have improved. The spacecraft have gotten more able to handle a wider variety of problems on board space, and been able to become more programmable, more adaptable. I wouldn't necessarily say more adaptable, but more reconfigurable. So there has been progress made there to make things more programmable and controllable in space. Now, I believe that the conventional approach is essentially to keep moving along in those directions, improve the bandwidth on board spacecraft, improve the number and quality of the rule mechanisms that you have on board the spacecraft, and then build their reliability up to the point where you can start to layer some of these other services on top, where you can There's a big effort into system resilience. So once you understand, once your systems understand how to control themselves and work on a fairly quick latency, don't have to phone home or be continuously commanded to do different things. What they're currently trying to do is to build a system that you can command, you understand what it's going to do, and it's going to provide a platform on top of which you can put the information systems and provide a platform that you can have these higher levels of connections, the services and the information services associated with that. There are some problems with that approach, in my opinion, that we looked at when we were researching multi-spacecraft systems at Goddard Space Flight Center. And one of the main problems is that every rule system that you put together is going to have its brittle nature. And that's going to provide some limits into how well your platform is going to hold together. That's a big problem, and it's shown up in a bunch of different ways when people are talking about making constellations of spacecraft do different things. You know, military constellations, spacecraft, missile defense. And so, do I think that we can get to a situation where you can build a networking platform from our space assets? Yes, I think you can. You will be able to do that. However, it's going to require some qualitative changes in the way that people put together autonomous systems.
Okay, that makes sense. Now, multi-purposing space assets and integrating or intermixing space asset which was sent 20-30 years ago and the ones which are going to which were sent only 5 years ago versus the one which will be sent 15 years from now. So do you see a huge gap in the manner of the format of the protocols that can be leveraged and handled with the space itself, or do you think they have to come down all the way to the Earth and one of the operations center does the translation and goes back? In this context, what I'm talking about is, for example, the LRO, if you do get an access to use some of its resources, and it has to kind of work along with maybe another 50 of the CubeSats that we may send to Moon. There may be interesting ways of using this combined assets for a contracted period of time. So during that time, do you see the complexity leading to resolution may be done at the op center down on the Earth, or we will be able to put adequate intelligence right up there and they'll figure out as they have to deal with the situation? Any thoughts?
I'm sure that when we bring in some of our communications and control experts into our discussions, they'll be able to share more detailed answers. However, when we're first starting out and we're first putting together our first networking experiments, they're going to be relatively simple, relatively straightforward, and we're going to be essentially taking baby steps using techniques that we already know and are already very comfortable with. However, that's going to change as the number of elements and the complexity of the capabilities, the complexity of our needs change. So when we start to add more and more nodes, more and more cube spacecraft, more and more rovers, you're going to run into the problems that we're talking. How do you build out a scalable system? So when you're first starting out and you just have a handful of nodes, you're going to be able to work with those, building on existing control technologies, building on existing control techniques. And then as you understand what happens with those, and as you experiment and learn from those, then you'll be able to start to optimize, improve the performance of those, develop ways to automate those sorts of processes, and eventually you'll be able to expand out your networking techniques. Particularly since we're going into this, we're going into this with the knowledge that yes, we know how to build scalable networks. We have an idea about how to build out from a small node network out to a larger node network, and we are going to be faced with simple problems well, relatively simple problems in the beginning, but it's going to be a learning experience, and we'll be able to learn and build out better networks as time goes on. And we've already seen examples of this. For example, with various kinds of autonomous operations and lights-out operations in our missions operations centers. For example, at Goddard, one of the things that we were talking about is a notion of perhaps graduated autonomy, or perhaps where the idea being that you increase or evolve the autonomy of your system as time goes on. And this is something that we were looking at in particular with our mission operations centers, where the autonomy, for example, doesn't necessarily have to be on board the spacecraft. You can also use some of those tools on the ground as well to help automate different actions that you're going to take. And one of the things that we were looking at was being able to take some of that automation, and then once you test that out on the ground, then move it to the spacecraft. So people have been looking into some of these questions for some time, and analogs exist, and we're going to take advantage of those in putting together the networks around the moon.
Excellent. Now, finally, what I have is a suggestion, or like a subject to continue with the discussion. Is it practical to build a facility which is essentially a network of resources down here on Earth, and some of them could be theoretically in orbit, meaning their visibility to certain ground nodes, it will maintain its periodicity associated with the orbital dynamics. Then it's like there may be heterogeneous capabilities sitting at various types of nodes. So I'm kind of thinking, is it possible that we model a lunar cloud right here on Earth that includes some of the numbers that we are kind of talking about, between 600,000 different nodes, and these nodes in reality could be one new server with what you call limited capability, which compares with a node we're kind of talking about, although these servers by themselves are able to communicate in huge chunk of data. Knowing the orbital dynamics and the limitations of the links that we are able to create, we can kind of deprecate its capabilities and the communication abilities. So to once in a while try this in Amazon cloud with 1,000 nodes is not a very big thing to do. And do you think it makes sense coming down the line as we are concurrently talking about the Deep Space Information System, a way to bring in simulated nodes and maybe even more likely live nodes which are actually prepared for the flight at a later date?
Well, first, we're coming up on the end of the hour, and I'm going to have to sign off at the top of the hour. But to answer your question is that there's a number of different ways to model and simulate. Simulation does not necessarily imply computer simulation. You can actually simulate a system with various sorts of electronics testing. For example, a lot of communications testing is done with signal generators where you modulate the signals in order to simulate what a particular receiver might receive when it's been deployed in space. So you figure out what you need to test, and you apply the appropriate modeling and simulation technology to that. It doesn't always necessarily have to be a mathematical model implemented on a computer. That's definitely true, for example, of network laboratories, where you could put together a ground-based set of routers, for example, or other sorts of wireless devices that you program with the protocols that would resemble the sort of protocols that you want to have in space, just to actually get some hardware together and see how that particular hardware solution behaved. So those are different ways that you can address some of the problems that are going to arise. So the answer to your question is yes. There are things that you can do on the ground to develop confidence in the different solutions that you're going to put together.
Okay. I don't mean specifically things like the transmission line characteristics, etc. But
Right.
the result of a impaired transmission will result in a packet which is not useful. So it's fairly simple at that level to not model the electronics, but loss of packets, useless packets. These types of faults are very much easily created in the network topology to get how we see the effect of ground stations, which is going to be around the Earth, some in the water, and many hops and jumps that may happen in the communication segment, that type of thing, just to kind of do.
Sure, and that's where some of the federated models come in. You can have hardware-based models, you can have software-based models. With regard to the federated modeling, you have models coming in from different domains, and then you're linking them together to form a more complete simulation or test of the system or the question that you're putting together. Okay, it's time for me to sign off.
All right, and thank you very much. We had a good one this time, and we'll look forward to the next one. That will be June 3rd, and that is going to be Moog John Howat talking about the Phantom Ride. All right, thanks for the viewers as well, and we look forward to continuing the next Hangout.
Very good. Thanks, Abraham.
Bye.
Okay, bye.